Okay, the next question I want to address is how much energy can we get from these? What is the cell voltage? Meaning, like, if I use this as a battery, how much energy can I actually get from this? And what we are measuring in that instance is called the electromotive force, or the EMF. It's the spontaneous flow rate. We're talking about spontaneous reactions of electrons from a high to a low. We kind of call it a pressure. Those electrons are going to flow to like even everything out. So that reaction happens. And it flows just like water. It's going from a high pressure or a high potential energy to a low potential energy. Okay? So it's always going to go, like I said, my electrons are going to flow from the anode to the cathode, because this is where we are going to be losing electrons. This is where we are going to be gaining electrons. So we call this one the negative and this one the positive. That's how a battery is set up. Okay, so to calculate the actual voltage, that's going to be the difference in the pressure or the potential energies. Okay, so it's just the difference between this pressure or this energy, and this energy. Okay, that's the electromotive force. We usually measure this in volts. Okay, 1 volt is actually a joule per coulomb. Joule being energy, coulomb being charge. So this is the amount of energy associated with how many charges are moving. Okay, so you can see we will measure in volts, but for conversion wise and making sure you know what the units mean, a volt is the same thing as a joule per coulomb, and coulomb is what we measure charges in. Okay. So essentially what we do is we say we need a reference, and we call this the reference one is the standard hydrogen electrode. So we just call hydrogen 0. So if you remember that reactivity series, hydrogen was kind of low on there. We call that voltage 0, and we measure everything against it. Now, when you actually do the lab, you are going to be using your own reference, and it's not going to be hydrogen. I believe that it is magnesium. So you're going to set magnesium as 0 and then compare everything to that. So the values on the sheet that you use for this section are not going to be useful in lab because you are making your own list. So just kind of keep that in mind. But what we usually do is, like I said, we set hydrogen as 0. And this is a hydrogen electrode. Because it produces gas, you have to use like a platinum wire, and you have to like collect the gas or make sure it's going somewhere. So we won't be doing this in lab, but that is the hydrogen electrode. Everything else is like a metal, so it's not too bad. So what I recommend doing is to print off the reduction potential sheet that is also attached in this lecture video. It will be extremely useful because I'm going to use all these numbers and you won't know where they're coming from unless you have this reduction potential sheet. Okay, so essentially what those are, okay, they are cell voltages for a standard cell. Now, a standard cell means everything is in a 1 molar solution. It's at 1 atmosphere and 25 degrees Celsius. So when we're asking questions in lab, like what could cause the cell voltages to be off of what you expect them to be? Well, we're probably not at 25 degrees Celsius, and we're probably not at exactly 1 atmosphere. And when you make these batteries or these cells in lab, the molarity is probably not going to stay 1 molar very long, because as the reaction starts happening, the molarity actually changes. So this is standard cell. This is what goes with what's on that sheet that you printed off. Okay. And how to calculate the amount of voltage for a specific cell is just the E naught of the cell, meaning the standard cell potential, is equal to the E naught of the cathode minus the E naught of the anode. So you just look up the number for the cathode, you'll look up the number for the anode, and it is the difference. Okay, so we were using this example, this zinc and copper example. If you look up zinc's E naught cell, it is negative 0.76 volts. And if you look up copper's, it is positive 0.34 volts. So I do the cathode minus the anode. Now the cathode was the copper, okay, cathode, red cat. So a reduction occurs at the cathode. So what was the thing being reduced? Well, the copper was the thing being reduced. It was going from this to this. So it's positive 0.34 minus negative 0.76. So you have to watch your signs. Essentially what we're doing is we're just looking for the difference between these two numbers. Okay, so it is 1.10 volts. That is the difference between 0.34 and 0.76. So like, what is that space? That is the potential difference. That is how much voltage we can get from this cell if we are at 1 molar and all of those things. Okay, so you have to actually look these up. Now, an easy way to tell which one is going to be the cathode and which one is going to be the anode. Okay, if you've got that list, essentially whichever one is more positive or higher up on the list, just like in the reactivity series, is the one that is going to go in the forward direction. That's the one that's going to be reduced. So let me pull that up really. Okay, so this is the reduction potentials list. Essentially, these are all the possible half reactions, and these are all their cell voltages. Notice this is called the reduction potentials list. So essentially these are all the reduction reactions. If it oxidizes, it goes in the reverse direction, okay? So whichever one is highest is going to go in the forward direction. So we were looking at copper and zinc, right? So let's find those. Copper is right here, and zinc is down here. Okay, so that means that copper, because it's higher up, it has a larger positive voltage, is going to go forward, which means it will be reduced. And then the other thing is going to end up going backwards, meaning it will be oxidized. So zinc down here, this one ends up going backwards. So one goes forward, one goes backwards. The difference between these two values is how much voltage you are going to get from that spontaneous cell. Okay, so the difference between 0.34 and negative 0.76, which is 1.10. And that is how we figured out the cell voltage. Okay, so what I want you to do for example number 4 is draw a cell of a cadmium and a tin. So you do have to figure out which one's going to be cathode and which one's going to be anode. Don't look at the answer yet. And then determine the cell voltage under standard conditions, as well as the oxidizing and reducing agent. So take a pause and give it a try. Okay, so this is how I like to draw them. You draw your 2 beakers. I've got my metal pieces. I like to put my anode on my left and my cathode on my right, just the same as the general, what's the word I'm looking for, notation, anode, cathode. As long as you label everything, you're good. They have to have a salt bridge, and I have to have which way my electrons are flowing, which is from anode to cathode. Okay, so now I'm like, okay, which is which? I got cadmium and I got tin. So I'm going to look at my reduction potentials list. And I would be like, okay, tin is right here and cadmium is down here. So that means tin is going to go in the forward direction. It is going to be reduced because this is a reduction list. Okay, so that's negative 0.14. And then cadmium is the one that's going to be oxidized, and it is negative 0.40. Okay, so I'm going to pull those numbers over. I said tin is the one that is going to be reduced. Reduction occurs at the cathode. It's a red cat. So cathode is tin being reduced. Okay, I pulled that number out. That's right here, 0.14, because it's cathode minus anode. Anode is essentially, I wrote the reaction backwards because that's what's going to happen. So I have cadmium is actually going to turn into Cd2 plus 2 electrons. And that one is negative 0.40. So negative 0.14 minus negative 0.40 gives me 0.26 volts. If it's not positive, then it's not a spontaneous reaction. Okay, so make sure you get a positive value for any voltaic or galvanic cells. So just a note about that list. Remember, they're listed in order of most positive to most negative on that handout. Okay, if I give you a question, I don't give you that list. Look at the values. The more positive one is the one that should go forward in the forward reaction, be reduced. And the one that's lower is the one that's going to go backward. Okay, so they are listed in that order, which means that the top left, because that's the one that gets reduced, is going to be a very good oxidizing agent. Remember, they're like opposites. Okay, and that means the thing in the bottom right, which is the thing that's usually going to get oxidized, is a very good reducing agent. Okay, so this kind of matches our list. You should have fluorine at the top, I think. Yes, fluorine is the best thing at being reduced, positive 2.87. So it is a really good oxidizing agent, whereas lithium is really good at being oxidized. So it is a very good reducing agent. Okay, so this kind of like summarizes how all of that works.